Okay, so we are going to continue our study for finding number of distinct elements in a stream. And at the end of our lecture last time, we saw this algorithm, which was like TS, which looked at the first C over epsilon square elements in the stream and outputs the number of distinct elements from here. Okay. So as I told you, right, like if there are more than C by epsilon square number of distinct elements, then clearly this is going to be a very like underestimate, right? And then using this, we made the following algorithm. So I made one mistake yesterday in the algorithm. This is why I thought that I should repeat it, okay, and then we will move to something else, okay. So instantiate, so we instantiated, if you recall, TS0, TS1, blah blah blah, TS log n, okay. So there are log n instantiation of this, that was the first thing, and then we choose a G uniform, we picked Z from 1 to n uniformly at random from two wide hash functions, right? And what did we do? And when ith element, and you know that all these elements are from 1 to n, right? So when we fed I to Ts, least significant bit of G of I. This is what we fed, right? So think of this as that there are like log n plus 1 different streams going on, right? Based on which is the significant bits we are trying to use, and we feed that to different streams here, okay? And then I just made a mistake. I said output, I should say I said output 2 power j plus sound, where t, so we can also use t tilde, the approximation, right? T tilde by 2 power j plus 1 equal to epsilon 1 over epsilon square, okay? So this is not right. This you will not get it correctly. So what we needed to say here is that this plus the content of that particular, okay, so this is basically Ts j, so this particular j, so whatever number of distinct elements this particular data structure returns you, Ts j, okay, times, so 2 power j plus 1. So content of Ts j times 2 power j plus 1. Notice, if I am going to always output 2 power j plus 1, there is absolutely no way that I can beat factor 2 approximation, right? And I was claiming that this gives you 1 plus epsilon approximation algorithm, right? So this is what, so this is the change which you need to make, okay? So I look at, so I do have a multiplier, but I multiply that with number of distinct elements which is there in the data structure TSJ, okay? And what is this TSJ? This is a data structure where I believe that the right estimate of T is there. And how did we get this T tilde? As I told you, right, we do have an approximation of T tilde, this factor 32 approximation, that is what we are going to use. So this T tilde is between real T over 32 times 32T, right? So, and this we know how to do it. So we are also going to run this in parallel, okay? Any question?
So the contents of other TSI,
no, they are of you. No, they don't matter at all. Think of this way, right? What did we do in a randomized algorithm, right? So so what did we do in randomized algorithm? All we cared about is which bit is set to 1, right? So if you are looking for a factor 2 approximation, it was good enough because you are multiplying with this 2 power j plus 1. That is exactly, so if you look at what did we say, that look at the jth bit, least significant bit. What is an expected number is there? Is this. This is what number of items which will be mapped to is t by 2 power j plus 1, right? So if I set j equal to say log t, what I'm going to get here? I'm going to get just one person, right? But that is like 2 power j plus 1, but that is going to be like some factor away from each other because this is an expectation. So now I only need to look in the content of that. This is why I don't need to sum up over everything else, okay? So what is the basic principle that we have used up until now? Let me go through that and then we will understand what is happening in all these algorithms. So we saw two algorithms up until now. Two algorithms. One was to count number of distinct items, number of items, and second was to count number of distinct items or distinct numbers. So what was the first step of these algorithms? We came up with an unbiased estimator, okay? So now what is an unbiased estimator? So first step is an unbiased estimator, okay? So what is an unbiased estimator? A random variable x is an unbiased estimator if expectation of x is what you want. Okay. So to count number of items, what was the random variable we used? We used, if you recall correctly, 1 over 2 power x minus 1, right? And we showed that this has a correct expectation, right? Then we used another random variable which was 1 over x minus 1. This also had a correct, what is that called? Correct expectation. So all the time you have to first come up with an unbiased estimator, which is nothing but set up a random variable whose expectation is exactly the quantity which you are looking for. That's the first thing, okay? But unbiased estimator alone is not good enough, right? We saw that its variance could be too much. So what did we do? Then second thing which we applied, and this is like generic to technique and tool. So first thing is we will see from now onwards that all the time we will try to set up an unbiased estimator for the object we are trying to estimate or approximate or count. And second trick which we applied is that do parallel repetition to reduce variance, right? So what did we do? So variance of just this estimator alone is not good enough. It doesn't gives you the kind of bound we wanted, right? So what are we looking for? We are looking for epsilon delta approximation. And what I mean by epsilon delta approximation is that probability that your object, whatever you are going to return, is right? So this is what it means. So like I'm not too far away from my estimator with probability at least 1 over delta, right? So this is the kind of, so what do we achieve in the second step? When we do parallel repetition, what do we achieve? We actually achieve, if you notice, that we are able to achieve this delta, we are able to achieve this one of these quantity, like we can achieve both here, but the dependency becomes 1 over epsilon square delta, okay? Then we applied median trick, right? What did we do? We said, okay, let's look at this particular algorithm, okay, and let's run this with epsilon equal to some 1/3 and delta. This is what we ran, right? We are succeeding again with probability delta, but it's just 1/3, right? And then we took median of all this, right? And we reduced the dependency on number of objects we have to compute to 1 over epsilon square to log 1 over delta, So this was the median trick, right? So you run this algorithm. So basically you are running first bunch of the algorithm, like you are looking at this estimator, which is the basic. I run it several number of times. I get something where I'm able to reduce. I generally apply with 1 by third comma delta or any constant success. You will apply this. This is why I call this a constant factor approximation. And then, but you could achieve both epsilon and delta at the same time, but the number of times you have to run this algorithm is roughly 1 over epsilon squared times delta. But just by doing a simple median trick, you can reduce the number of times you need to run to 1 over epsilon squared log 1 over delta by doing the median trick. Meaning you run this good algorithm with good several number of times, log 1 over delta times, and then apply Chernoff to say that you are able to achieve 1 plus epsilon approximation with this probability, okay, by using median trick, okay. So these are the three basic steps of most of the algorithms, numerical algorithms that we see in streaming algorithm. Come up with an unbiased estimator, do a parallel repetition to get a constant factor approximation. If you directly are able to get a constant factor approximation, you don't have to do parallel repetition, then you can do directly this. For example, here we directly came up with a constant factor approximation. Our unbiased estimator itself was a good constant factor approximation, then I did not need to do this parallel repetition, right? Then I directly went to these kind of boosting to get 1 plus epsilon approximation. Okay, so that should set up the plan for most of the things which we want to go and have a look. Okay, okay. So now we are going to see.
So second step also we are taking the mean rate of many.
Yes.
And even third step we are doing that. So can't we do it in the second step only doing more number of?
I told you, right? You do it, but this is what it takes. Right? So imagine, okay, so as I told you before also, right, I mean one can do it with log 1 over delta, this is a good question, with for some random variables in some instances you can do it, for certain times you can't do it, because what happens that I first make some good algorithm and then I take median of that, okay, versus I make lots of bad copies, bad algorithms, and then I take the median of that, okay. So these are two different things, and how they work I actually don't know. How they play against each other, I don't know. Okay. So now I want to move to proving some lower bounds. Okay. So as I promised to you is that okay. So I'm going to now show to you that for number of distinct elements, deterministic and exact, if we are going to use, then we are going to use some min of omega n comma m bits. Okay, and now let's see how do we go about proving these kind of lower bounds. And the great thing is these are unconditional lower bounds. They are like from pigeonhole principle, right? Not even communication complexity, nothing. Okay, so what I would like to spend next 35 to 40 minutes is to show lower bounds. So for number of distinct elements, counting number of items, we said that hey, if you are looking for an exact algorithm, you cannot have less than log n bits, because any algorithm which uses s bits, 2 power s must be greater than or equal to log n. So like 2 power s must be greater than or equal to n, so f must be greater, because otherwise if there are n items, 2 items you will map it to the same number, right? Okay. So, but I would like to apply exactly the same kind of idea for the number of distinct, counting number of distinct numbers, but it is not as obvious as this. So what is my first theorem going to be? So my first theorem is going to be is that no deterministic exact, okay, just to set up, okay, no deterministic exact algorithm for computing number of distinct elements computing number of distinct elements there is in lit O of min m comma n bits. Okay. So you cannot have lit O of, does not have any deterministic exact algorithm for computing, and when I say in this streaming setting, for computing number of distinct elements in these many bits. Okay. So the proof I'm going to give you is something very interesting. Suppose I have an algorithm A, okay, that is both deterministic and exact and takes S bits of space. Okay, so this is the space content. Now I'm going to use this algorithm. Okay, I'm going to use this algorithm to do something interesting. So what I'm going to do, I'm going to establish a function from 0, 1. So I'm doing min m comma n, but the kind of instances we will create m and n are roughly same. So it will automatically imply the same kind of lower bounds. Okay, so I'm going to give you a function from 0, 1 to n to 0, 1 to s that is injective using A. If I can give us such a function, what does it imply?
Injective on what?
From 0, 1 to n to 0, 1 to the power s, where s is the s bits of space. If I give such a function, then what happens? Huh? Then, right? Because there cannot be an injective function from a larger set to a smaller set, right? So this is just basic pigeonhole principle, right? So we are not going to use any communication complexity or nothing. We are just going to show such a function. Okay? Okay. So this is our our objective. Okay. But we will use so this is what you will see, but I'm going to use the word called encoder and decoder. Okay. So what is encoder going to do? It's going to take some x in 0, 1 to n, and is going to output some sort of streaming, because look, A is a streaming algorithm, right? It takes stream as an input. Given a string x, it is going to create some stream for this particular algorithm. Okay. Okay. And what is decoder going to do? Decoder will be given a memory content of this algorithm A, right? So given y, and what is y? Y is a memory content of some x when memory content of some x when encoder x is run on A. Okay. Now to give an injective function, if I can show to you following, then I'm done. What should I show to you in terms of encoding? Okay. If I can show to you for all x decoding is this, then am I done? Then have I shown that this function is injective, right? So encoding of x, it takes x and whatever this guy is going to map, okay? So what is the mapping? Mapping is basically will be some space content run on this. This is my mapping will be, right? But if I show to you that for all s, so what will be my mapping here? So as I told you, right? So I have this algorithm A, given an x, I have an encoding, so I run my streaming algorithm. On that, whatever the memory content, as I told you, it is at most s bits. So whatever that s bits is what I'm going to store. So f of x is going to be, okay, is going to be memory content of A encoder of x. This is what is going to be my f of x is, right? Which is a s bit information. So this is what it is going to be. So now I have to give you, but suppose if I show to you for all x, decoder of encoder of x is x, have I shown that the function is injective? Okay, think about it. So to show that function is injective, all I care about is this, because decoding of two things, I mean, is going to be different. Okay, so what is my encoding function? What do you think should be the encoding function? Hey, I mean, A is a streaming algorithm for counting number of distinct elements over 1 to n, right? And I haven't given a 0, 1 to the power n bits, right? So what is x? This is it, right? X is element of this. What should be the encoding of x? Can I get blue pen?
Yeah, I do.
See, now you have so much pen.
You sent me, no?
Yes, not mail, I call them. It's very simple. I need 1 to n.
All positions where x is 1.
1, that's it. Right? So, right, I such that xi is 1, that's it, right. So this is all, right. So all the positions where xi is 1, so let's call it xi, so where x is like say x1, x2, xn, so there are n bit string, right. So if some position is this, so that position I am going to, so this is my string, okay. So this is my encoding. Now I should give you a decoding algorithm, right? So what do I have? What do I have for decoding algorithm? I have a memory content for some encoding, right? What do I have? A memory content of some encoding, right? So here's my A, which has been run on some stream, I don't know, like some encoding of x, which you don't know. All you have in hand is y, which is a memory content of A. Now based on this y, I have to give you a decoding algorithm. How am I going to do that? I'm going to decode this x1 to xn bit by bit. If you think it's a quite, I mean, there's no step in this algorithm which is very amazingly difficult or hard. It's like really simple thinking. So first thing what we should try to know, with the help of this, I at least can know exactly how many distinct elements are there. This we can know, right? Because looking at this memory content, I can definitely say how many number of, like whatever the query algorithm associated with, I can know how many number of distinct elements are there, right? So okay, so this I know. Now what should I do? suppose you knew X. I mean, I allow you to feed X, but I will not show you X. Okay. Suppose you have an access of, like you have an access of this A, you can run as many times A as you like. Okay. But I will not show you X. Okay. But I have an X. Trust me, I will feed the right X all the time. But now you need to tell me what else do I need to feed that I can get information about something.
We can feed 0 1 to the power n minus 1, and if number of distinct counts,
And flip a 1 to 0 or something.
That you don't have no access to. Right? All I said to you that if you tell me that, hey, run encoder of X plus something, I will run for you. But whatever I do with X, and I'm look, this is a deterministic and exact column, so this will give you a correct answer.
So you're trying to construct decoder.
Decoder, yes.
So all you know is S bits.
All you know is S bits. This is what you know, right? So look, any algorithm, okay, so for example, what would happen if I ran A on this? What will it tell me?
What is dot I?
I mean, like, no inner product. Like, it's like this is the next element in the stream, where I is like 1 to n. Right? So encoder of X is some set of strings, like set of numbers, right? 1, 3, 5, 7, that you have fed. Now I'm also feeding I to it. If I fed this, what information will I get?
I was not there then.
So I will get, if I was not in encoder of X, then what will I get here?
Plus
F0 plus 1. If I was element of encoder of X, then what will I get? F0. So have I decided what ith bit is now? Look at the ith bit. If that bit was set to 1, then encoder of X, as Venkatesh described here, this I is fed to that streaming algorithm, right? And we are feeding I again. So the number of distinct element is not going to change. Right? In that case, I know I was set to 1. But suppose it was set to 0. And now, so encoder of X or this set does not have I, right? And this was 100. And now I put I at the end. So it is a distinct element than encode anything in encoder of X. So now it will tell me 101. Right? That is F0 plus 1. So by running this algorithm here, right, I could fix ith bit was 0 or 1. Is the idea clear? Right? So, but now, I mean, I don't have encoder of X, but I have Y. So basically what you do, look at A and you have Y, you just stream I now and it will tell you what is the new memory content, because all you have is Y. So the way it works is that here is my A at this point of time and it has Y. So it's like, this is how the current state of this algorithm is. I feed I. Now Y will become some Yi, and based on that I can encode this information, right? So basically because of this, now I can completely recover X from which this Y was created bit by bit. Okay, is there any question? Right? So look, if I know the memory content of Y, right? So after whatever was streamed here, based on that, all the memory it has is Y. it forgets. This is all that this algorithm can remember. Now I feed I, so whatever it remembers, now it has to do something with y, unless that content be called yi. Now based on this content yi, I can get this information on this information, and again, so I will run this for all I in 1 to n, right? So now bit by bit, so I will start with this width. If this is what is 1 I mean, or this is what you mean 1, what doesn't matter what you mean, you just stream these numbers, each of this, and based on that you will get 1 0 0 1 0 0 1, and this is an unique encoding. So what did we learn from here? So if, and like look at this stream, right? I mean, since this is a function from 0 comma 1 to the n, I mean number of distinct elements, at least in this family, could be as many as n itself. So m and n are related to each other here. So what does this proof tells us? This tells us that if we are looking for deterministic exact algorithm for computing number of distinct elements, then you need omega min of m comma n bits. This is like at least n. I mean, this is not even big O or nothing. You need at least n bits. Okay. So this is how you do, right? So you learned how to. So you try to set up some sort of injection, and now I mean, but this is only when I allow exact and deterministic. Next, we will try to do approximate and deterministic. Okay, question. Now we will do the same business, but we need to have certain structures, properties. Okay. And there are certain things which I on purpose leave at a gap, at least so that the people who are scribing should make an effort to do it yourself. Okay, that's a part of exercise. So please don't ask me for my own notes because they are all over the place. Okay, this is just for make me understand. I don't have very organized notes. Okay, so now let's move on to doing the next thing. Okay, so what do you would like to prove now? So now the theorem which I would like to prove, I want to say any deterministic algorithm for computing any deterministic algorithm, say that any deterministic algorithm that computes number of distinct elements, say within factor of 1.1, okay, requires omega n space. And again you can say that m and n all will be related to each other. So this is my whole goal. Okay. So this is what I want to do. So now what is given to us? Deterministic and 1.81 approximate. Okay. And suppose takes s bit of space. So I definitely want to give a mapping from here, but this is not what I want to give a mapping. I want to give a mapping from some family C, okay. But suppose I am looking for an omega n bit space, and this is the kind of scheme I want to use. What is the properties of C do I need? Okay, let's try to write what kind of properties of C do I need. So do you understood this all the scheme, right? This is what encoder decoder will do. This is right? And this is what fx will be memory content of encoder of x and all those, okay. So let's write it down some properties of C, okay. So suppose I said omega n, and let's say omega n would have been n by 3 bits, exactly. What do I expect cardinality of C to be? At least how much? If I want to prove a lower bound of n by 3 bits, what should I expect? And the scheme is same. Given this family of C, I'm going to give a mapping from this family of C to 0, 1 to the power s such that it is injective, right? If that is my scheme and I want n by 3 lower bound, what should be the cardinality of C should be? Why did you get n bit lower bound in the previous case? Why did you all of you suddenly said 0, 1 to the power n to 0, 1 to the power s? If you give, then definitely s has to be greater than or equal to n. Why was that inferred? But I understood that 1-1 mapping, but you inferred. So last time I wrote here 0, 1 to the power n. If I give such a mapping, then you said, hey, s is greater than or equal to n. Why? So either you did not understand that, or you didn't understand my question now. Something you did not understand. Something you did not understand. Why? Is it a wild guess, or why?
Because if this is less than n, then two elements from the input will be because of Piaget principle, if s is less than n, then two elements from 0 and 2n will be mapped to
That still doesn't give my answer.
we want it to be injected.
If it is injective, then what is the meaning? If I have a function from a to b and s is injective, what can I say?
Size of b is greater than size.
Size of b is greater than or equal to size of a, right? Which implies 2 power s is greater than or equal to n, and that is why I got s is greater than or equal to n. Okay. Now I said, okay, fine. Now here it is. I'm going to give a mapping from some family C to this, such that I'm going to get a lower bound from n by 3, and this is an injective function. So now I'm asking you, what is the cardinality of C? So if I apply the same argument, then what I want 2 power s should be greater than or equal to, this is like, I know this is like s is at least n by 3. So this cardinality of C should be greater than or equal to 2 over n over 3. If it is less than this, then things wouldn't work out. Right? So there is no, I'm not like, because it is approximation, I'm not using anything. So one thing is clear, if I want n by 3 bits, then I need to have size of this should be roughly equal to. Okay, fine. Okay, so we'll create lots of space, something of this nature. I don't know what the constant is, so let's put Cn, some constant. Okay, and this C is going to be, subset of 0 to the power 1 n in for now, let's believe me that this is a subset of 0, 1 to the power n, and encoder of x in C is same as before, is that number of places this is blah, is I xi is 1, okay. Now, so this is my encoding scheme, okay. What kind of decoding scheme? How could I, with the help of this, now I only have 1.1 approximation, how on earth do I go about doing these things, you know? Do you get my point? Like, all I have is 1.1 approximation algorithm. What property do I need to have about objects in my sets, okay? Or look, or if it is inconvenient, let's put it that psi is subset of 2 power n, like, which is same as 0, 1 to the power n, like, doesn't matter, okay? So they are like sets of indices, okay, between 1 to n, so they are sets. Now, I want to have something of this nature, but look, I was just one object, right? I mean, if on stream of size n, if my memory content takes s bits, on the side of 2n size stream, it is going to take 2s bits, so order s bits or something, okay? But all I am trying to do is decode it, okay? So now, how am I going to decode? So last time we were trying to decode bit by bit, but now this is going to be some subset, and I want to know whether whatever y is, this is an encoding of the x which I have in my hand, that's it. But how do I verify it? So I ask myself a question, okay? I ask myself a question. So suppose I have C, I know this C, right? I know this C. So suppose I have some excess element of C, and here is a y which is a memory content, and I have a question. What is my question? What is my question? My question is encoder of XS is the memory content y belongs to encoder of XS. Right? So if I ran A on encoder of XS, is this y? The y what I have in my hand. I want to verify, I have a set. I said, is this y same as XS? Okay. Now let's ask ourselves a following question. Fine. So now here is your sum x with respect to which you have memory content y, okay, and now I append xs, the set which I have in my hand, okay, and for brevity let's assume that it will be useful for us. Every set in C has length, say, alpha n. So every set has length exactly equal to alpha n. Let's believe that first, for now. If x is equal to xs, how many distinct elements will I get? I have f0. Based on y, I have f0. Right? So suppose if I fade xs and xs is equal to x, what will I get? if they are same, then I'm going to get n by 50 or alpha n plus minus whatever little variations I have, because whatever that y is, it's like some approximation, right? But notice if x and xs content are same, like stream is same, what I'm going to get is f0 plus minus the error term, which is like 1.1 f0. This is what I'm going to get. But if they are not same, and if they only would have differed at say 1 bit, it's very hard to distinguish between this XS and this. But suppose I told you that any two sets do not overlap too much. Then what happens? If any two sets do not overlap too much, then suddenly when I put XS, right, number of distinct elements just booms up. And then even if I do little bit of error, it will be much more than if I would have put the same string. So I can distinguish whether it is XS or not by if I had properties that any two sets in my family overlap very little, right? If I can ensure that any two sets in my family overlap very little, right? So when x and xs are same, it will be something like f0, right? But if they are, and what is f0? f0, since everybody is alpha n, it is going to be some alpha n plus minus 1.1 alpha n. This is what it is going to be, right? Because every set has alpha n elements, right? So this is what it is going to be. Now suddenly, if the two sets are different, it is going to be 2 times alpha n plus minus 1.1 times 2 alpha n, right? This is going to be way too huge number compared to this number, right? Imagine yourself that each set has size n by 100. For example, let's just say, just put some number n by 100, okay? And I told you that S intersection T for any S comma T, let's just do some computation, is less than equal to n over 10,000. 10,000? 10,000. Suppose I prove this to you. Then what happens? If I prove this, that any set S intersection T is n by 10,000, then let's see what happens to this computation. So I have this f0, right, which I know. So now I put xs, suppose x and xs are same. Then what will I get? From here, I will get n by 100 minus plus minus, what is 0.1? Is 1 by 10, right? So n over 1000. This is what the variation will be, right? So then my number will be n by 100 plus minus n by 1000. This is what my this. But if I put this different than this, then let's see how much variation will be. First, let's count them. So they have how many distinct elements will be there? Like the different S intersection T is like n by 1000, which is minuscule compared to the distinct elements they have, which is like say n by 100, so n by 50, roughly n by 50 distinct elements I have, and then n by 50 plus minus some 1/10 of this is going to be how much? 500, right? Like they are like two things which are poles apart. So if I can find a family with a property that every set has same size, pairwise intersection is huge, then we can use this encoding decoding scheme to check whether whatever y I have belongs to this or not. Look, this decoding algorithm is going to take exponential amount of time because I don't know what X content it is. So I have to run over every string in my C. But that is not the point, right? All I was doing is giving such a map, right? So there's nothing about running time, there's nothing about any of these things, right? So what was an idea? Look, when it was exact, we were able to distinguish by just one bit. Okay, did you plus one or not? Now we have some approximation. So we have to create enough gap when if this is what it is or if this is what it is, so they are so far apart that I can, by looking at this, I can distinguish it is this situation or it is that situation, right? This is what we do when we do hardness of approximation. We create gap. Either you are of this kind or of that kind, and there's a gap between these two so that we can distinguish, right? So this is what we aim to achieve, okay? Okay. So the sets which we need, okay? So at least I told you what the plan is, more or less. So I'm going to suppose I had the lemma, so with some quantification, lemma, and then we will prove this. There exists a family C subset of 2 power n satisfying two power Cn for all S in C n over 100 and for all S not equal to T in C n by 2000, which is less than equal to mod S by 20. So this is the family I will construct, right? This is my family. So now, so from this family I will give her, right? So suppose I had such a family. This is my lemma and I have been able to construct this family. So my encoder function is what? Strings of this, right? Encoder, so x in C, what is my encoder of x? X itself, right? They are like indices 2, 3, 5, 7, 9, which can be fed to my algorithm. And what is my decoder? So as I told you, right? So let's do decoding. As I explained to you, we will use the fact that things are nice. So what I'm going to do, so what I have F0 and Y, the memory content of A run on some encoding of X in C. And our job is to figure out what this X is. Figure out what X is. Okay. So now what we'll do is as follows. Okay. So for all, let's call it XS in C, okay, we are going to run what? So A and Y, okay. You run XS here, okay. It is going to give me some number, right? Let's call this Y XS. So when I run this, I get Y XS. And now based on these two numbers, right, what do I have? So let's call this, based on this, I get a number, let's call it F0 of XS. So when I run, so this is the number of distinct elements in total. So now I have two numbers. I have F0, I have F0 XS. And now I want to check whether the memory content Y corresponds to XS or not. Because if it corresponds to, then I can get this. Okay. So I check, right? So what is the property, right? So now if x is equal to xs, if x would have been equal to xs, this is the stream of x, this is x of s, then what will we get? Every set has size n by 100, right? So as I wrote before, what I'm going to get? N by 100, I'm going to get some number n tilde, which is going to be n by 100 minus is 1.1 approximation, right? So minus n by 1000 times n by 100 plus n by 1000. This is the case if x equal to xs. Fine. If x is not equal to xs, then what do we know? These two sets intersects at most as n by n to the power n by 2000. So the total number of elements is going to be, distinct elements is going to be at least say n by 50 minus n by 2000, right? N by 2000, right? This is number of distinct elements is at least this much, right? And now let's call this n star, right? At least this n star. Now my new n tilde is going to be n star minus n star by 100 times n star by 100 plus n star by 1000. If n is large enough, these two are very, very different cases, right? So if this is the number which I am getting as an approximation, I'll say, well, no, this is different than this. If this is what I'm going to get, I will say, no, this is what it is. So by going over every element in C, I can decode, okay? So if we had such a family, then with the help of such a family, I can give such a mapping with encoding and decoding function. So it all boils down to finding such interesting set of family, okay? And all I need to show that such families exist. I don't even need to give you like a constructive proof to make this. If such families exist, we know we cannot have such an algorithm. Because if, I mean, it's all existential, right? Because I'm just saying that, look, if you had such a great algorithm, then if I had such a family, from that family I could give you such a function, right? So it's all exist. So all I need to show to you that such family exists. I do not need to give you a constructive algorithm to do this, okay? And if I have to do existential proof, what tools do we have? What tools do you know to show such a family? Yes, the only word which we all know is probabilistic method. Okay, so is now let's forget all these things and let's focus on proving this lemma. Okay, okay, good. So at least, look, I mean, this is just some maths, but the moral of the story is that to prove lower bound of certain kind, we need to establish establish a sort of injection function from a family of set to 0, 1 to the power s, where s is the space taken by your algorithm. If you can establish from certain family, then that provides you a lower bound by just simple pigeonhole principle. Okay, so that's the moral of the story. Okay, now what is the second moral of the story we need? Whenever you have approximation, when you have exact 1 and plus 1 is able to differentiate between things. When you have approximation, you need to have two things, one here and one here, far apart that you can distinguish. Oh, if I am here, I must be into this case. If I am here, I must be into this case. I cannot be close enough, then I cannot distinguish. And that's a basic principle which is applied in any deduction whenever you have approximation. Okay. Question. Okay. So now we want to construct such a family. Okay. And I want every set to have size n by 100. Okay. So what I do, I make a bucket of 100 each. Like I write 1, 2, 3, n. So first bucket consists of first 100 number. Second bucket consists of 101 to 200 and so on and so forth. So how many buckets do we have? N by 100 buckets. And now my any x in C has a property that suppose this is bucket 1, bucket 2, this is bucket n over 100, right? And assume that n is power of 100, like n, like 100 divides n or something. What is the property of x into say? That x intersection bi is exactly equal to 1 for all I in n by 100, right? Then clearly every set has size how much? N by 100. So this is perfectly fine, right? Okay. So what we are going to do, we are going to create a set x1, x2, xn, where how do I create xi? Okay, it selects, or let's say xj, it selects an element from bi uniformly at random. So it just picks one of the element of this set uniformly at random. So this is how I'm going to create x1 to xn. I will tell what this n is. Okay. So this is how I have created my set. We have to just show that we can create large enough sets to prove these things. So by construction, what all properties are satisfied? This is satisfied for sure because we have the way we have built. What is not satisfied is this. Okay, let's ask ourselves. So let's pick up two sets, S and T. Okay. So I want to know what is an expected intersection of S intersection T. Okay. What is an expectation of S intersection T? Or I mean, let's say XA intersection XB. Okay. What is a, okay? So let's set up some random variable. Okay. What is random variable? 1, 2, n by 100. And what are these random variables? Right? YABJ is 1 if XA intersection XB, if XA intersection XB intersection BJ is 1. So if they intersect in the jth bucket, then I put 1, otherwise 0. Because anyway they are going to pick one element there, so the intersection is going to be 1. Okay, so this. Okay, so let's compute. So if you notice, what is the expectation of this cardinality? Is nothing but summation over expectation of YABJ, j going from 1 to n over 100. Do you agree? This is what it is, right? By linearity of expectation, I can write this intersection as sum of these random variables, and this is what it is. So all we need to compute is a probability of this. What is the probability that YABJ is 1? Hey, these sets are random sets in the sense, in this it picked up one of these elements of this guy with probability 1 over 100. Other guy also picked up the same element with probability 1 over 100. So this is 1 over 100 into 100, right? So 10,000. Correct? It is 1 if this also is the same element and it picks, and they are independent. So this is 1 over 10,000.
There are sum of 4 all there.
What? What?
There are 100 elements.
Yeah. Okay. Into 100. Yeah, either it is this, that. So what will we get? 1 over 100. Fine. Okay. So what is an expectation? So what is an expected intersection? So what is an expectation of XA intersection XB is n over 100. Did I do something correctly? No. It's not n by 100 times 1 by 100, right? Which is n by 10,000, right? No. Yes, it is n by 10,000. Come on. Okay, fine. So pairwise intersection is this, okay? Okay, so now what is the probability that XA intersection XB is greater than 5 times its expectation? Apply Chernoff. It will be some e power, right? What is this? Some e power, some minus c prime, like some c prime. This is not important, okay? I mean, some constant. I will not penalize you if you just write like this, it's fine, okay? And what we have applied is Chernoff. Okay. So I'll be done. No. I'm saying all we have been able to show at this point of time, probability that for a particular pair A comma B, I mean it varies a lot from its expectation is exponentially small. So what is the probability that there exists a pair I comma there, okay? But what are we interested in computing? Probability there exists A comma B in 1 to n, whatever this 1 to n, there exists A comma B in n such that XA intersection XB is greater than 5 times expectation of, I mean I should write here, right, XA intersection XB, otherwise it doesn't make sense, okay. Expectation of XA intersection XB is what? Is less than, by union bound, n choose 2 times expectation e power minus c prime n. And what we want this to be? If I show that this is less than 1, then am I done? If I show that this is less than 1, then am I done? Then what I have shown to you? Then if this is less than 1, it means there exists x1 to xn whose size is, whose everyone is this n by 100, and for all s and t their intersection is at most n by 2000 because that is 5 times this, okay. And all I need to show is that to show this, all I need to show is that there exists some, I mean n is large enough that this will cancel out with this, or smaller than this so that it is less than 1, that is it, okay. So there exists some n for which this happens, okay. So what we have been able to show, such families such that there exists exponentially large sets, family of sets such that each of them are size n over 100 and their pairwise intersection is at most n over 2000, okay. But look, this is the way I ruled out 1.1 approximation. You can also rule out 1.5 approximation, but in omega n, the constants will differ, right? As we know that, like, if we are looking at log square n, then we can get little o of n space algorithm, right? So there will be some trade-off, like worse approximation you want to rule out, the less amount of space you can prove that you need. Like lower bound, like the lower bound on the number of bits you need will keep reducing. So they are inversely proportional to each other. Better like worse approximation can only rule you worse space bound. Okay, questions? So I have shown you a spectrum of algorithms doing this. Okay, now I have 20 minutes left. Okay, in this 20 minutes I will do something very different. So if you have any question, please tell me now. All clear? Excellent. Okay, so this method is called probabilistic method. Methods. If you want to know more, you read book by Epsilon and Spencer. And this method was made famous by Paul Erdős. Okay, this is all that I can say to you. So there are lots of existential proofs of this kind which is known. Okay, okay. So now let me move to something different. Okay, so you notice I use the word F0. I started to use the word F0 in my this thing. Okay. Okay, so notice what up until now our streams has been insertion only, like we were just inserting some numbers. Okay, but there are situations where numbers can come and numbers can go, right? So they can appear and disappear. So the model which we have studied is called insertion only model. Okay, so all the upper and lower bounds which we have given up until now is about insertion only model. Okay, but there's something called Turnstile model. Okay, for these numbers. Okay, Turnstile stream. So what is a Turnstile stream? Okay, so in Turnstile stream, okay, you are given x in some Rn. Okay, okay. So in this model, we would like to see x in Rn. So you start with all zero vector. What is this? This is all zero vector. All zero vector. And what is an update? Okay, and each update is of the form I comma delta, okay, where delta is in R. Okay, so what does this corresponds to? It corresponds to, so think of this as x1, x2, dot dot xi, xn. This corresponds to, well, xi is now xi plus delta, right? You update the ith bit or ith location with delta, right? So now imagine, now if I wanted to compute some things, and like one can come, one can also go, like because delta is the element of R, so things can go up and down. Okay, and what is my objective? Okay, what is my objective is that want to compute / approximate some f of x where f is some function, right? So that's our objective, that we would like to compute some function here. Okay, so how can we model our distinct elements thing in this model? So right, so in distinct elements, right, if xi comes like this, like we will always be doing I comma plus 1, because we are only talking about at this point of time what we did, like insertion only, right? So I plus 1. So if xi comes, I will say, hey, go to the ith bit and increase by plus 1, right? And what is the function f you want to compute? Now, what is the support of this vector? Like how many number of non-zero elements are there? That's all that we are computing, right? That is nothing but L0 norm, and this is why it is called F0. So we'll get to that. So this is exactly why this is called F0. Okay. Okay. So to do this, we are going to move to a completely different technique, which at least we saw in the last streaming course about linear sketching. Okay. So we saw lots of sampling up until now, 2 kinds of sampling. So how was those sampling working? Those sampling were like estimators, like unbiased estimators, and we were doing something. But now we are going to do something called linear sketching. Okay. So it is also going to be like sampling, but bit more. So what is, now we are going to the linear sketching. Okay. Unfortunately, this is the only known technique to attack these problems up until now. There are no other known techniques to solve these kind of problems. Okay, the kind of problems we are going to solve. It's actually only. Okay, linear sketching. But do you know why it is called Turnstile model? I actually checked Wikipedia last night why it is called Turnstile model. Not that I got it, but I at least. Do you know what turnstiles are? What? So, okay, have you seen some buildings where things keeps rotating? Like you go in and then things rotates and you go inside. So this is that is what is called turnstile. So you can go in and you can also come out, and this is why it is called turnstile model. I mean, and who gave this name? Muthu Krishnan in 2005. So at least I did my research on. I mean, it's good to know history. I mean, why something is called something. Okay, so now back to our linear sketching. So what is a linear sketching? So linear sketching is basically you store y equal to some pi x, where pi is element of R m cross n. So it's some matrix. It's a m cross n matrix. It's a short and fat matrix. Okay, what I mean by short and fat matrix is m is going to be way smaller than n, right? Okay, so but it should worry you. If we are going to have n bits of space, and if we are going to store this matrix pi, which has like whatever it is, I mean it has some mn entries, right? And if you are going to store this pi as pi, then we have whatever it is definitely going to take more than n bits. So hoping that we can do many of these problems like distinct elements in small space is, I mean, it's not possible. So generally what happens that this pi's are not given explicitly, but these pi's are given in a way that you can read its column easily. So you can read, like, very easily you can construct an element of pi, okay? You can construct very easily, a column or an entry of pi, okay? So notation always is very helpful. So let's call it pi 1, and I mean columns, pi 2, pi n, okay? Okay. Another way to get this pi is basically these pi's are constructed using pair by, like, some wise hash functions, okay? So like, what will be this first row? I will say, hey, this is nothing but n to blah, and it is pi of I is nothing but a x I or something of this nature. Like, you understand my point? But we'll get to those things later. But suppose I ask you a very simple question. If I gave you this, right, and you have y, and all I tell you that I can give you pi I. So if you ask me pi I give you an access to pi I. You cannot ask me for anything more. And suppose y is given, which is nothing but pi x, right? You have y, and I, like, this you don't see, this pi you don't see. But if you ask me, give me an ith column of pi, I will give you this ith column of pi. And suppose some update has come. What has come? Some update has come, I comma delta. How can you update y? You get my question, right? I have y, so you see y, this is given to you, right? But y is like some pi of x, so now, right?
We know pi of it. We know pi of it before the update comes.
You know y, so you know pi x, yes, you know y, you know pi x, yes.
So I ask the ith column of pi.
Okay.
And add pi I delta and add it to 1. Because pi x is sum of columns of pi multiplied by
Correct,
x I.
right? So what you are saying? So what you are saying to me is that we can do as follows. Y, new y is going to be pi x plus, now look, I only want to add to the column of I, right? And I have pi I, right? Then maybe I should multiply this with, what is it called? Vector where you have ith bit is set to 1, ith bit is set to delta, and delta times ei. Is that what we want?
Just pi and delta.
Pi I? Yeah, that's also fine. Right? So if I give you a column, you can update y very easily. So it's all about how to get these things, right? So as I told you, right, that one way of storing these things are using hash functions, right? So what it will be, I'll say, hey, look at the first row, it is given by two wise independent hash functions. What are meaning of two wise independent hash function? Then all I am storing for this guy is, say, a1 and b1, right? Now if I know a1 and b1, two log n bit object, then I can know what this is, right? What is this? Because I know it is a1 of x, like I plus b1, right? Similarly, for the second row, if I had, say, a2 b2, I can know what this element is, because ith entry I am looking for is nothing but a2i plus b2, right? So on and so forth. Now if you notice, if each of these columns, each of these rows are given by some 2 wise independent hash function or some 4 wise independent hash function or 10 wise independent hash function, the amount of space to store these rows succinctly is going to take if I am going to use k-wise independent hash function, so k times m times log n bits, right? This is what it is going to take, right? So this is a succinct way of doing this. So in many of the applications, m is going to be roughly like 1 over epsilon square, k is going to be some constant, so this is going to take you some log n epsilon square space to store all those things, right? In all our application where k will be like 4, 5, 10 and m will be like 1 over epsilon square, okay? Okay, and now generally what we try to do, so okay, so the problem which we are interested in is what is called, so let me at least tell you the problem, and next time we will give an algorithm for this. So the function f which we are interested in computing is what is called frequency moment. So now we have gone to something called moment estimation. So let me just tell the problem and then we'll stop. So what is moment estimation? So what is FP? Given x, what is FP? It's basically it is pth norm, which is summation what? This is what it is, right? Okay, so this is what we are interested in. Okay, so this problem was first studied by Alon, Matthias, yeah, and Sigid in stock 96. Okay, and there is a very beautiful, amazing transition for P. So what is known, and we will see both, that P between 0 and 2, right, if you are looking for 1 plus epsilon approximation, it is going to take you order log n over epsilon square space, and this is tight. But the situation changes drastically for P strictly greater than 2. So what is known is this is theta, so this is like lower bound, n to the power 1 minus 2 by P, like poly log n over epsilon square for 1 plus epsilon approximation with probability 2/3, right, with probability 2/3. Okay, so there is a kind of jump in complexity at P strictly greater than 2. Okay, so what AMS gave is for P equal to up to less than equal to T2. So what we will start next time is I'll give you an algorithm for P equal to 2, which is easy to understand. And as always, we will use a sketching algorithm where each row will be an unbiased estimator for this, right? So each row is going to be, I'm going to come up with set up a random variable such that each row will correspond to computing F2. You understand my point? Like it's an unbiased. So expected value of this is going to be the exact value F2. Now what is each row going to be is like same property, but how many of them are there? 1 by epsilon square of them, right? So this is like we are doing the second step of this algorithm, repeating it, right? But again, the idea for all these algorithms remain the same. This matrix also, each row will correspond to establishing a proper unbiased estimator for all these things, and then we will see how many M we do need to get all these kind of properties. Okay, so that's a goal for next week. Okay.